The general trend for orbitals is that the energy of the orbital is going to increase as n increases, as the principal quantum number increases. Remember back to the guitar string analogy. You pluck the strings harder, you end up with a higher overtone, which has a higher energy. Same thing is true for the principal quantum numbers. So for the hydrogen atom, the energy distribution is going to look like this. You can see that in the hydrogen atom, you have everything laid out according to principal quantum number. You start with n equals 1 at the lowest possible energy, and you have the 1s orbital. You go a little bit higher in energy, and you see that the 2s and 2p orbitals are all at the same energy, right? N equals 2 has the next highest energy. If you go up again to n equals 3, you see the 3s, the 3p, and the 3d orbitals. And I'll use this diagram to briefly highlight the differences between shells, subshells, and orbitals. So the shell in this case is everything with the same principal quantum number. So the 3s, the 3p, and the 3d orbitals all belong to the same shell. That is the n equals 3 shell. All of the 3d orbitals that are grouped together on the entire set of d orbitals is referred to as a subshell. And by the same argument, the grouping of p orbitals is the p subshell, and the grouping of s orbital, just the single one of them, is the s subshell. So s is odd, where the subshell is also the orbital. And within subshells, you have individual orbitals. So you can have a single d orbital within the d subshell within a given shell. And as you've seen in other videos or in your textbook, each individual orbital within a subshell gets its own designation. So for the d orbitals, those are things like x squared minus y squared, dxz, things like that. For the p orbitals, they're just px, py, and pz. So I could give you a designation 3pz, and you should be able to identify that this is a single p orbital within a p subshell within the n equals 3 shell. Now, this is the diagram that you get for hydrogen, which has one proton, one electron, nothing else. And as soon as you get more complicated than hydrogen, the whole arrangement of orbitals is going to change. As soon as you get more complicated than hydrogen, now you have more than one electron. And remember that electrons are going to repel one another. So in something like helium, with its couple of electrons, or lithium with its 3 electrons, or whatever, all of those electrons are going to be interacting with one another. They're going to have electrostatic repulsions as they push each other apart. And these electrostatic repulsions are going to shift the energy levels of the various orbitals within what we call a multi-electron atom. And what this means is within each shell, all of the different subshells are going to have different energies. So what you can see is the orbital energy levels start to cross one another. It starts out looking pretty similar. The 1s starts everything off at the lowest energy. Then you get a grouping of n equals 2 levels in the n equals 2 shell. But now you can see that the 2p orbitals, the p subshell, is a little bit higher in energy than the s subshell. And it's okay, it's not enormously different. But then you get up into the n equals 3 and n equals 4 levels. And you see that the energy levels start to cross each other. And what you find is the n equals 4 s subshell is actually lower in energy than the n equals 3 d subshell. And as you go higher and higher in your n values, you see this crossing pattern continue. And there's an easy way to work out the order of these energy levels. So you start by writing in numbers that effectively just represent the principal quantum number, and then you add in the different types of orbitals according to the column. So the first column gets the s's, second column gets the p's, and so on. And if you want, you can expand this diagram to include the n equals 5, 6, whatever principal quantum numbers. But this small version will work for demonstration purposes. So you draw this diagram, and you start drawing diagonal arrows from top right to bottom left. And you can use this to work out the order. So you start at the top. The 1s subshell is first in energy, and then you follow the arrows. So the 1s is first, then the 2s is higher in energy, and then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, then the 4p, and so on and so forth. And you can see that this corresponds to the order for the energy level diagram that I've shown you, where 1s is lowest, then 2s, 2p, 3s, 3p, 4s, 3d, and then 4p.